Assalamu alaikum. Today we want to talk about chapter 23 entitled Lipids. And we will cover the following sections: structure and classification of lipids, fatty acids and their esters, properties of fats and oils, chemical reactions of triacylglycerols, phospholipids and glycolipids. Now, what are lipids? They are defined by solubility in nonpolar solvents, which is a physical property rather than by chemical structure. So lipids are compounds that are insoluble in water but soluble in organic solvents. There are many different kinds and they serve a variety of functions in body. Many lipids have hydrocarbon or modified hydrocarbon structure, properties and behavior. Lipids can be classified into two general types, the open chain type of lipids and the cyclic lipids. We will discuss all of these as we go. Now here are some examples of lipids here. A wax, as you can see here, this is triacylglycerol. Here the parent compound is glycerol. You can add this fatty acid once, twice or three times to get a triacylglycerol, and this is the storage form of lipids in our body. And cholesterol is sterol, which is characterized by having these 6-membered ring plus this 5-membered ring fused together. And also here we have the prostaglandin compounds with physiological importance in human. Naturally occurring fats and oils are triesters formed between glycerol and fatty acids. As I said, glycerol is the parent compound of triacylglycerol. Fatty acids are long, unbranched hydrocarbon chains with a carboxylic acid group at one end. Most have even numbers of carbon atoms, 16, 18, 20, etc. Those without double bonds are saturated, and those with double bonds are unsaturated. In naturally occurring fats and oils, the double bonds are usually cis rather than trans, and this puts a king in the hydrocarbon structure. Chemists use a shorthand nomenclature for fatty acids that avoids using the common names. The notation uses C for carbon followed by the number of carbon atoms present, then a colon and the number of unsaturated bonds present. For example, palmitic acid C16,0, stearic acid C18,0 are the most common saturated acids. 0 here means 0 double bond. Oleic C18,1 with 1 double bond. Linoleic C18,2 with 2 double bonds are the most common unsaturated ones. In addition, we have polyunsaturated fatty acids. They have more than one carbon-carbon double bond. And this table shows us this. Here we can see here structures of some common fatty acids. We have the two general types, saturated and unsaturated, as you can see. Lauric, 12 carbon. Here we see the number of double bonds, all zeros. Myristic 14, palmitic 16, stearic 18. Now here we have a property here called melting point. Now as you see, there is an increasing there is an increase in the melting point of fatty acids with increasing number of carbon chain, 12, 14, 16, 18. So you see which one has the highest melting point. It is stearic because it has the largest number of carbon atoms. Also here we have unsaturated, as we said, olive oil 18, 1 double bond. Linoleic 18, 2. Linoleic, soybean and canola oils 18 and 3 double bonds. And then arachidonic animal fat, 20 carbon with four double bonds. Now here we can again look at the melting point. You see here, melting point decreases with increasing number of double bonds, as you can see here. Again, there is a gradual decrease in melting point with increasing number of double bonds this time. So know this property. If you are asked which of the following has the highest or the lowest melting point, know that. For example, also you can compare between مثلا stearic 18.0, Oleic 18.1, linoleic 18.2. All of them have the same number of carbons, but this is 0 double bond, this is 1 double bond, this is 2 double bonds, and you see again there is a decrease in the melting point with increasing number of double bonds, as you can see. Know this property. Now, triacylglycerols, animal fats and vegetable oils are the most plentiful lipids in nature. Animal fats are solid, whereas vegetable oils are liquid, but their structures are closely related. All fats and oils are composed of triesters of glycerol, 1,2,3-propan-triol. This is the IUPAC name, if you remember, also known as glycerin, with 3 fatty acids. So here they are named chemically as triacylglycerols, but are often called triglycerides. And this is their structure. Then glycerol is, let's see this. You see, this is glycerol, our parent compound, plus 3 fatty acids, we form triacylglycerol. Then glycerol, you add the 3 fatty acids, you get triacylglycerol. Again, the fat or oil from a given natural source is a complex mixture of many different triacylglycerols. Triacylglycerols can be simple or mixed. Simple if all the 3 fatty acids are the same. If the 3 fatty acids attached here, they are the same, then this is called simple triacylglycerol, like مثلا, or they can be different. If they are different, then this is called mixed triacylglycerol. Then it could be simple or mixed. And the mixed could be saturated plus unsaturated fatty acids on the same molecule of a triacylglycerol. Triestyrene is an example of a simple triacylglycerol, triestyrene, where all the fatty acids are stearic acids. Vegetable oils consist of mainly unsaturated fatty acids. Animal fats contain a large percentage of saturated fatty acids. This difference in composition is the primary reason for the different melting points of fats and oils. Now, the more double bonds a fatty acid has, the lower its melting point. As I showed you when we compared the C18 stearic with 0 double bond, C18 with 1 double bond Oleic, and C18 2 double bonds linoleic, and we found there is a decrease in melting point as the number of double bonds increase. So the more the double bonds a fatty acid has, the lower its melting. Now the difference in melting points between fats and oils is a consequence of this difference. Now vegetable oils are lower melting because oils generally have a higher proportion of unsaturated fatty acids than animal fats. Then this is the reason. Then vegetable oils have lower melting. Why? Because oils have a higher percentage of unsaturated fatty acid in relation to animal fats. Now again, if we look here, this is a saturated fatty A saturated fat has only a carbon-carbon bonds and appears straight. This is stearic acid, an 18 carbon saturated fatty acid. And here we have unsaturated fats bend. Why? Due to cis double bonds. إذن قلنا naturally occurring fatty acids, unsaturated fatty acid, they have cis configuration, and this double bond is cis, and cis puts a kink. It's no longer a straight chain. You see, it puts a kink here, like in linoleic acid. So here an 18 carbon unsaturated fatty acid. You see the difference between them? Now the hydrocarbon chains in saturated sites are uniform in shape with identical angles at each carbon atom, and the flexible chains showing them to nestle together. Now unsaturated acids, fatty acids, have rigid kinks wherever they contain cis double bonds. The kinks make it difficult for such chains to fit next to each other. The more double bonds there are in a triacylglycerol, the harder it is to solidify. And again, this is a fat and this is a oil. You see the difference. Now, triacylglycerols are uncharged, nonpolar hydrophobic molecules that coalesce when stored in fatty tissue. The primary function of triacylglycerols is long-term storage of energy. As I told you, that triacylglycerol is the storage form of lipids or fats in a human. Where it is stored? In adipose tissue. Then adipose tissue serves to provide thermal insulation and protective padding, and it is the place where triacylglycerol is stored. Imagine an average adult 70 kilogram weight has enough lipids or fats in its adipose tissue to let him survive 40 days without eating. Color and flavor are contributed by natural materials. Now, oxidation causes rancidity, decomposition to products with unpleasant odors or flavors. Then sometimes you say this is a rancid oil with unpleasant odor or flavor. This is due to oxidation. What happens in this double bond is oxidized, and decomposition to products with these unpleasant odors or flavors. Now, what are the properties of the triacylglycerols in natural fats and oils? We have they are all nonpolar and hydrophobic. Means, hydrophobic means water hating. No ionic charges. Triacylglycerol is a neutral molecule. Solid triacylglycerols, the fats, has high proportion of saturated fatty acid chains, whereas liquid triacylglycerols, the oils, they have high proportion of unsaturated fatty acid chains. So the more percentage of unsaturated fatty acids in triacylglycerol, the more it becomes liquid or oily, and the more the percentage of saturated fatty acid, it becomes solid. Now, what are some of the chemical reactions of triacylglycerols? First, we have hydrogenation. The carbon-carbon double bonds in vegetable oils can be hydrogenated to yield saturated fats. Margarine and solid cooking fats are produced commercially by hydrogenation of vegetable oil. You heard about oil hydrogenation to convert it to margarine. By controlling the extent of hydrogenation and monitoring the composition of the product, consistency can be controlled. So here what you do is you saturate the double bond. How? By adding hydrogen. طبعا hydrogenation by using hydrogen on a catalyst like مثلا nickel or palladium. Exactly as you can see here in this example, this is a partial structure of an unsaturated vegetable oil. Here you see the two double bonds here. you need 2 moles of hydrogen to saturate these double bonds. شايفين we have 2 double bonds, you need 2 moles of hydrogen with palladium catalyst. Then you see you saturate, you convert the double bonds into single bonds, all of them. These are the 4 hydrogens atoms that come from 2 molecules of hydrogen gas. Then this is called hydrogenation of oil to form a margarine. You convert unsaturated fat to saturated one by this process called hydrogenation. A second reaction called hydrolysis of triacylglycerols. Triacylglycerols can be hydrolyzed in the body. This hydrolysis is catalyzed by enzymes called hydrolysis and is the first reaction in the digestion of dietary fats and oils. So there are enzymes called lipases found in the intestine. They tend to hydrolyze these triacylglycerols. Dietary triacylglycerols are hydrolyzed by lipases in the intestine. Whereas we have other lipases in the adipose tissue that they also tend to hydrolyze triacylglycerols into what? Into 1 glycerol plus 3 fatty acids. Now, the alkaline hydrolysis of a fat or triacylglycerol is referred to as saponification. Now, soap making involves the base-catalyzed hydrolysis of a triacylglycerols. Any mixture of triacylglycerols can be used. The second ingredient needed is lye or potash. You can use sodium hydroxide or potassium hydroxide for this purpose. So, what are the results of the saponification of a triacylglycerol? You get also glycerol but plus 3 soaps. In the hydrolysis, you get glycerol plus 3 fatty acids, but in saponification, you get glycerol plus 3 soaps. Now, phospholipids and glycolipids. Now, cell membranes separate the aqueous interior of cells from the aqueous environment surrounding the cells. The 3 major kinds of cell membrane lipids in animals are phospholipids, glycolipids, and cholesterol. And here we can see this example, glycerol 3-phosphate. You see, this is called glycerol, alcohol in glycerophospholipids, and here you find a compound called sphingosine, alcohol in sphingolipids, and the location of phosphate in sphingomyelin, as we will see. So the 3 major kinds of cell membrane lipids in animals are phospholipids, glycolipids, and cholesterol. Now, phospholipids are built up from glycerol to give glycerophospholipids, or from sphingosine to give sphingomyelin. So, if the parent compound is glycerol, then you have phospholipids. If the parent compound is sphingosine, then you get sphingomyelins. Now, glycolipids are also derived from sphingosine but have an attached carbohydrate. From the name, glyco and lipids, you have carbohydrate and lipids. So, then sphingosine but have an attached carbohydrate that is a monosaccharide or a short chain of monosaccharides. You could have one sugar or several number of sugars, as we will see. Now, however, cholesterol is a sterol. It is a class of biomolecules that are characterized by a system of 4 fused rings, as I showed you before. Cholesterol is a fatty substance. Now, again, phospholipids, like soap and detergent molecules in having ionic, hydrophilic heads and hydrophobic tails. Then phospholipids, like soap and detergent molecules, they have an ionic or hydrophilic head plus hydrophobic tail. They differ, however, in having 2 tails instead of 1. Then phospholipids, they are characterized by having two tails instead of one. The glycerophospholipids or phosphoglycerides, again glycerophospholipids or phosphoglycerides, triesters of glycerol 3-phosphate, the most abundant membrane lipids. Two of the ester bonds are with fatty acids. Now the third position is a phosphate ester linked to ethanolamine, choline or serine. Let's see. If we look here, some glycerophospholipids. Now if we look here, you see this is our parent compound, and here we have a phosphate group is added at carbon 3, and then we have X. This is the rest of the polar head. Now depending on the nature of X, then we have the type of glycerophospholipids. Let's see. Precursor of X, if it is H, okay, then we have phosphatidate, basic structure of glycerophospholipids. Then this is formula of X is H, and this can come from water. Water مثلا is HO2, H2O. H2O can be written like this, OH, then we have H here. So if this X is H, then it is called phosphatidate, and this is the parent compound or the basic structure of glycerophospholipids when X is equal to H. This is called phosphatidic acid or phosphatidate, naming of resulting glycerophospholipid family. Now if the precursor of X is choline, and here we have OH and then X, if this is choline, then this is called phosphatidylcholine. And the function, it is the basic structure of lecithins, most abundant membrane phospholipids. If X is ethanolamine, then it's called phosphatidylethanolamine, membrane lipids. However, if X is the amino acid called serine, then we have phosphatidylserine, and this is present in most tissues and abundant in the brain. If the precursor of X is myoinositol, like this, then we have phosphatidylinositol and relays chemical signals across cell membranes. So these are some types of the so-called glycerophospholipids family. And the names here, remember, phosphatidic acid or phosphatidate, phosphatidylcholine with +1 charge, phosphatidylethanolamine with a +1 charge, phosphatidylserine with 0 here, and phosphatidylinositol as you can see here. Then these are some glycerophospholipids, and they differ only in the X. Then X identify your glycerophospholipids. This is called phosphatidyl. This is called phosphatidyl. Either phosphatidylcholine, phosphatidylethanolamine, or phosphatidylserine, or phosphatidylinositol. Now, glycerophospholipids are named as derivatives of phosphatidic acids. Lipids with a phosphate ester to choline are known as phosphatidylcholines or lecithin. So, another name of phosphatidylcholine is lecithin. Know this. Then, lecithin is another name of phosphatidylcholine. Hydrophobic tails and hydrophobic head groups make glycerophospholipids emulsifying agents. So again, here you have, this is your phosphatidate, and then here if you attach choline here, it becomes a phosphatidylcholine. Remember, this is the form that exists in physiological pH. So what is the net charge here? -1 + 1, it is 0. So a phosphatidylcholine or a glycerophospholipid that is a lecithin has a net charge of 0. If you put here, for example, ethanolamine, if you put this in this inositol, then it's phosphatidylinositol, and so on. So these are the various structures. Now, in sphingolipids, the amino alcohol sphingosine provides one of the hydrophobic tails. Then in sphingolipids, the parent compound is sphingosine, and this is the structure of sphingosine. You see, here we have amide link, here we have fatty acid acyl group, here we have this is called sphingosine. Now the second tail, then this is one of the hydrophobic tails. Now the second tail is from a fatty acid acyl group connected by an amide link to the NH2 group in sphingosine. You see the backbone in green, this is the sphingosine, and these are attachments. You see? Now sphingomyelins are sphingosine derivatives with a phosphate ester group at carbon 1 of sphingosine. Now the sphingomyelins are major components of the coating around nerve fibers.